The broadcast is now starting. All attendees are in listen-only mode.
Hello, ladies and gentlemen. Good afternoon. Thank you very much for your time and staying online while we were sorting out our technical issues. We had a small issue with our IT system, so we were not able to share our screen and to call in. So we will start right now. We apologize for the time consumed, and we are happy to join. Just as a practical thing, I will ask my colleague, Mr. Nizar, to support me in sliding the slides. So hereby, Nizar, can you please continue with the next slide? So thank you very much. Before we start, some standard information. Please feel free to ask any questions during the session. We will record those and we will try to answer them during the session as much as we can to address your comments. You can do that by your text box on the site. For today, our session, process automation and the use of solenoid valves in process applications. We have roughly 5 different topics we would like to discuss with you. During this masterclass, we will not go into the very details of the topics, but we will at least give the opportunity to go over the function, the design features, where are the topics we can look into to have a well-designed system for your application and use of solenoid valves. First of all, we would like to start with the working principle. Next slide, please. So the function. Solenoid valves are commonly used in the process industry, and actually there are 2 options which we can do. And process valves with the solenoid function are mainly used for automating an on-off signal. This can be done by an electrical current, which we call the steering signal. The solenoid valve that's being used to control the circuit, to open and close the process line, is mainly focused on compressed air, oil, water, but these also can be gases, for instance. Compressed air is the main topic of today because we are focusing on the solenoid control valve that is operating quarter-turn actuators, for example, linear cylinders. But as we also start soon with the next example, you can also see that the same design principle can be used to control, for example, a water line or an oil supply line for a certain application and process. If we think about pressures, we not only look into positive pressures, but there are also the possibility to control vacuums. So in terms of the spectrum and also with festo-hour range, we are mainly looking from -1 bar, which is a vacuum, up to +90 bars. But even more and higher pressures can be achieved in certain cases. For pneumatic systems, we mainly work for 4 to 8 bars to drive and control pneumatic equipment. And at the same time, the ambient environments are averagely between -20 and 50 degrees. Certain cases, they can be higher, especially outdoor applications here in the Middle East. So also these items and these topics need to be considered when designing a system, because a solenoid coil, which we will highlight a little bit later in the session, will go into the generate heat, and this heat generation also need to be dissipated into the ambient temperature environment. So to have a good temperature difference, we need to size the coil on the environment where it's being used to. But first of all, the working principle. So first, the design what we have within solenoids is the so-called direct operated valve. In this design, the entire force to open and close the valve seat, which in this case is the little small green piece in the water line, will be operated and controlled by a magnetic coil, which is the gray to reddish part in your screen. And by applying an electrical force on a magnetic coil, which is generating a current, will move the small little plunger upwards. This will mean that the water flow from port number 1, which is the supply, will open the environment to the outlet part. This is a very basic display about the solenoid valve, and used also in many applications. It's mainly for what we call 2x2, so 1 supply, 1 outlet, but there's also used in the more comprehensive designs. The second design, what we're using, is an indirect operated solenoid valve. In this design, the supply pressure of the medium is helped to make the operation suitable. And what does this mean? As you also already can see between the two pictures on the left and the right, you see there's a big difference in the size of the solenoid coil. This means that in the indirect operated design, we use a much smaller coil, which also means we are generating a less electric force. But at the end of the day, the same pressure needs to be activated between the two valves. So in order to achieve this higher force, we are using a little bit of the supply pressure, which comes from port 1, and we have a tie-off to a small pilot section of the solenoid. And what we actually did is we built a small valve into a valve. And by only controlling a small part of the flow, so not the entire outlet, the forces are much smaller. And by use of doing this, we are able to control the main body, which is the gray large poppet design of the valve, which closes off port number 1 with port number 3, with only a small current. The benefit of this is that we can build much smaller products, which is much more compact, but also the voltages can be kept relatively small. When we are not applying a certain pressure, a certain current, the solenoid valve will switch back in its neutral position, and this is achieved by springs. Also in the diagram in the side, you see that there's a spring being used to switch the solenoid back into its neutral position, which means in this case, for both valves, the neutral position is normally closed. That means if no current is applied, the supply from port number 1 is blocked off to port number 2. So this is the basic design of the solenoid valve and the concept how it's working. But there are also certain designs of solenoid valves. And first of all is the design principle. In order to switch the channels between the chambers from the supply port and to the working ports, certain channels needs to be blocked off. Otherwise, we have no control about the flow. And in the pneumatic solenoids, to control an air supply to pneumatic equipment, we have mainly two designs, the spool design and the poppet design. One of the most common designs these days is the spool design of the solenoid valves, which relies its basis of a plunger, which is moving within a certain tube, and this tube have connections with the different channels. And here you see in the middle, the dark blue part is connecting different channels together. By moving this plunger in the middle from left to right, we are able to block off the different channels and guide and direct the flow to the different areas where they are required. The benefit of this is that there are smaller coils. We also use less force to operate this design principle. At the same time, also with the less forces, also less friction is seen. But there are also some cons on this part, because it's a very highly precise machined piece of stainless steel and aluminium with a very small opening orifice in between. Also, you see sometimes we make use of some O-rings, but in general, there's always a little bit of a small air gap. And this means that also sometimes the very small leakage flow is seen with these type of valves. This leakage flow is because of its compressed air. It's not like seen as a massive number. It's a very small percentage of the total supply pressure. But it is possible, especially with valves that are a little bit older, start to leak a little bit of air because the wearing after thousands of cycles has been worn out a little bit, or particles have been slipped in between the seals. So for the majority of the applications where air quality is well maintained and correctly applied, these valves are really effective and can be used in also compact solutions to have a high density of solenoids in a certain area. Another design is the poppet design. With the poppet design is a little bit more basic, but also stronger and robust valve. It's larger and also higher forces are needed to operate this valve design. And mainly you can see on the right picture on the side, the poppet design needs to be seen. Everything is in a circular way. These are round holes. that an orifice is open and closed by a rubber seating. So this seat moves and opens the channel left to right in this case. So on the left side of the picture, where this is the section view, you see there's mainly an open channel. By moving the plunger to the left side, you see that the other channel will be opened, and this is the switch. These valves are mainly used for applications where air quality is a little bit less. You can think about, for example, into the cement industry, where a lot of dusty particles are being seen, or applications where less lubrication is used to seal off and lubricate the piston going into the solenoid valve. In these type of applications, poppet valves tend to be a little bit more robust and stronger, having a stronger design for switching and operating the cycle. Of course, they're bigger, they're a little bit more stronger built, so in general also with the design this needs to be considered. At the same time, if you compare these type of valves, because the movement of the piston is relatively small, also for higher airflows, the right valve needs to be designed, because with the same connections, a poppet design valve might have slightly lower flow capabilities than a spool type of valve. And last but not least, between the cycles, it is possible that sometimes two channels are commonly connected to each other before the next channel is sealed off. So this is also one of the topics that we have a terminology. There might be a small amount of overflow possible during switching and operating of the spool design. If we go to the next slide, we would like to go now more into the design and functions. So there are mainly 4 different designs in the industry. We started our session already with the 2x2 valve design. This design is mainly used for fluids and gases, and it's a monostable design. In the middle part of the example, you see also the example and a case how this product looks into the real-life applications with the threaded connection. A monostable valve is a valve which has a single coil and will be, by use of a spring, will be positioned to its neutral state when it's de-energized. This, as I mentioned, is mainly for fluids and gases, where there is no return. So when the flow is being stopped, everything in the line and also the working port number 2 will remain at the moment when the valve is being closed. More seen into the process industry, for example, to operate single-acting actuators, is a 3x2 valve design for single actuators, which is also by default a monostable valve. Again, we are using a single coil to operate the valve. The difference is with the 2x2 valve that there will be a so-called return port or bleed valve in certain cases, where the compressed air, which is generated and supplied into the energized state for port 2, will be released through port number 3. So this is one example for single-acting actuators, where also the actuator will be returned by a mechanical force. For double-acting actuators, and we also have this as a view later on a little bit more in detail, we are using also a slightly larger valve, because there are 2 ports that needs to be energized and supplied by compressed air. So if we see here, the valve has now not only 3 connections, but is having 5 connections and 2 positions, open and closed. Again, in a monostable valve, there will be a spring which defines the basic position of the solenoid valve, and by energizing the electrical coil, you will see that the switch is being made, and ports number 1 to 2 will be changed to connect port 1 to 4. The return ports to release the compressed air from the channels from the previous position will be used by both port number 5 and port number 3. One difference is, and that's something as well, is the bistable valve. So a bistable valve will not rely on a spring, but will rely on an additional solenoid coil. This valve design is also in many cases used by the 5x3 design. This means that not only 2 states are being possible, but in this case actually 3. And this means, for example, an open position and a closed position, but also a blocked position when the valve is not being energized. For example, for locking functions, this can be one of the possibilities, so that all the channels are closed and nothing goes in and out to the chambers. Both for the 5x2 and for the 3x2, we have bistable valve designs. And bistable valve requires two coils, always, and will need to be defined if it's normally open or normally closed. Also, the next picture, I believe, if we switch the screen, we will see the example of a bistable valve for a 5x2 valve, where two coils are being applied to change the state of the solenoid valve. Okay, so how does this look in real life? So here we see a basic arrangement of a solenoid valve operating a single acting quarter turn actuator. This means from port number 1, where the compressed air is supplied, this is currently blocked by the solenoid valve because the electrical coil is not energized. All the compressed air from the cylinder to open this actuator is currently being reduced to port number 3, so the actuator is freely able to move to its natural position. When the electrical solenoid coil is being energized, we see that there's a shift. That means that the air supply will be connected with port number 2 on the outlet, and the actuator can be opened. So when we go one slide back, we see once the coil is de-energized, we see that the compressed air from the outlet port is brought back to the return port. So all the system behind the solenoid valve is depressurized. Standard design of a single solenoid with a single acting actuator. If we go and look into a double acting situation, here not a single line goes to the actuator, but we have two different lines which go into the actuator, knowing port number 2 and port number 4. The air supply coming from port 1 again will be connected automatically to close the actuator. And currently the outlet port of the cylinder is moving to the return port. By energizing the electric coil, currently the channel from the air supply will be connected to the actuator, and the return port has the possibility to return and depressurize over port number 5. So this is also the switch of the actuator that for a double acting actuator will switch on and off. So in basis, this is how the concept works. Next slide, please. Connections and interfaces. One of the main topics of connecting a solenoid valve, there are multiple designs. So if we see the next slide, there are mainly 3 standards which we would like to work and explain with you. So to connect a pneumatic solenoid valve, one of the most standard conditions in standards we use is an individual threaded connection. This means that a single solenoid valve will be mainly connected with threaded fittings, and from these fittings, tubing will be used to run through an actuator or a cylinder, and will be completely individual. Typical sizes for these valves is 1/8 till 3/4, in certain cases 1-inch connections for the very large valves. These connections can be BSP or MPT connections, but there's always tubings and fittings needed. Especially for the process industry, where we deal with quarter turn actuators, there is a certain NAMU phase developed according to VDI VDE 3845. This NAMU interface specifies the connection between the solenoid valve and the actuator. So these will always fit together in a way that they cannot be interchanged. These ports will be aligned to each other, and there will be a direct connection. This means that less fittings are being required to connect the solenoid valve to a quarter turn actuator. The 2 working ports, which you also can see in the middle of the valve, will be directly connected to the pneumatic actuator. Like normal individual connections, we mainly are standardized on 1/8 to 1/4 connections. These again can be VSP or MPT threaded connections. But the main difference is that the NAMU solenoid valves are directly installed on the actuator which avoids a lot of tubing, individual tubing, but also the possibility that tubes can break, fail, or can be less equipment that needs to be installed at the facility. The last one, which is a standard, the ISO standard, the 55991, is a standard to identify the pneumatic connections of a solenoid valve with a certain manifold. This is not the same as the NAMUR interface design. NAMUR is a German organization for the process industry. The ISO standard is a generic institute to standardize interfaces and requirements in the industry. The benefit of this interface is that depending on the ISO size used, 1, 2, 3, or 4, of 4 is being the largest, this interface can handle all types of valves that have been designed as per this ISO standard class. So even though if you have an installation where you have an ISO standard, but no Festo valves are being installed, it's always the possibility to remove the old valves and replace the new valve, for example with Festo, to this specific manifold. The benefit of this is that you have a lot of flexibility in your installation, and also for MRO spare part activities, urgent replacements, this interface allows you to directly place and install a replacing solenoid valve to your installation to increase the troubleshooting at that moment. Still, from the manifold, tubings and fittings are needed. So there still will be fittings, but because they're having a manifold interface, these will not be directly installed on the solenoid valve, but through the manifold. One comment with this, because we know we are mainly talking about direct links, we always recommend to use flow control valves. Flow control valves, for example, a push-in design or an inflow design for the NAMU interfaces, these valves allow for a proper airflow for the return ports, which is crucial to control the opening and closing speed of the pneumatic actuator. Not being used, that means that there will be the maximum speed, which is possible by the design, will be generated. And in certain cases, it can cause for damages because equipment is switching too fast, or in the process industry, this results in water hammer. So to avoid these cases, we use flow control valves to precisely control the opening and closing speed of the pneumatic actuator. Next slide, please. A new design these days is the use of valve terminals. Instead of having all the solenoid valves individually connected on the pneumatic equipment and the pneumatic items, we can then individually connect them on a pneumatic aluminium header with individual connections. Again, with the first picture, individual electric connections. All of the solenoid valves are individually connected to the main PLC. So there is a certain level of integration, but this integration is mainly on the terminal level. But for larger applications where more valves are used, this is already a very good step forward. This avoids to place a lot of different solenoids within the certain parameters of the pneumatic actuators needed. The only thing is more wiring is required because each and every solenoid valve has at least 2 to 3 lines to be connected with the PLC, which means more PLC outlet cards are needed. Another technology is to use the benefit of a valve terminal with a multi-core connection. Again, you see the different solenoid valves on a row. They are, here in this case, these are almost 8 units with the pneumatic connections in the bottom side of the terminal. So each and every solenoid is supplied by compressed air through a main connection with also combined return ports, the silencers on the white units in this case. And from the individual connections from the solenoids, the connection can be made through a pneumatic tube to the actuator within the field. The benefit of this, there is one single point of control with a multi-core cable. This means that there will be one single common line and all the individual lines are connected with one of the solenoids. So less cabling and a more compact design can be achieved. Another benefit within this design, and in this series of Festo, as you can see on the screen, we can also sometimes use double valves in one housing. So on this part where there are two blue buttons, this can be that there will be a 5x2 bistable valve, or there might be the use of 2 times a 3x2 valve within one housing. This means that more compactness can be achieved by building and using such a valve terminal. Nowadays, also field bus communication becomes more and more important. So instead of using a multi-core cable, which still requires to use a lot of digital in and outputs on your PLC design, we are using a field bus node, which communicates through the most industry standard communications standards with the main PLC, which means that each valve terminal needs to have a power supply as well as an interface with the main PLC. This reduces a lot of wiring within the field and has the benefits of the compact design and the flexibility of multiple solenoid valves into one manifold. So these are mainly the different designs we can have, and like the individual solenoids we've seen just before, also for these type of configurations we always recommend to use flow control valves with your solenoid valves to control the opening and closing speed of the pneumatic actuators. Coil characteristics. So this is one of the topics that to make the connection possible and to make the switching feasible within the solenoid valve, we need to use an electric coil. So electric coil, this is powering the solenoid valve. Within the industry, we are using mainly two types of currents. So direct current as well as the amplified currents for installations where more power is required. When AC currents are being used, we are looking into a frequency between 50 and 60 Hertz. So if you see at the graph, just down below, there's a pure AC curve where there's a fully plus and fully minus into the voltage drop we see. Another current many times used is the direct current. You see this in the top, which one of the supply lines is always positive. This voltage is mainly used for lower voltage systems, and this is also why we mainly see ranges between 12 volts, 24, which is the most common in the industry, up to 48 volts. It's a less risky installation, but this is also why we see, for example, the use of these voltages with intrinsically safe systems, known by the blue cable glands of the solenoid valve. But in certain cases within the industry, it's possible that longer cable lengths are required. More power is needed to operate the solenoid coil because of its size. So in these cases, always we use the amplified current design because we can transport more voltage over longer lengths of distance of cable. If cables gets longer, they have the tendency to have a certain loss through to the resistance. And to overcome this and to still have enough voltage and current available at the end of the line, the higher amplified current is being used. Because of the solenoid coils are generating a magnetic force based on electric energy, it's important that also the temperature is being considered. So each solenoid coil is having a certain temperature range to operate around 50 degrees, 60, 70 degrees. It's important to always keep this in mind when selecting the right solenoid coil for the application. Used in hazardous and demanding applications. So we already just touched the topic just before, but in this last topic of the session, we would like to discuss also those locations where it's a little bit more demanding. Yes. So when it comes to hazardous and demanding applications, how do we classify these? So the first topic we always would like to say, and we would like to refer to, is the protection of the solenoid coils. So in this example, we would like to start first of all with how to protect our equipment and how to protect our environment. The first standard we're using is to refer to is the IP rating. Although the solenoid valve itself is a purely mechanical item that controls and switches compressed air or a fluid, the electrical part, where IP is also having a rating on, is mainly on the coil relation. So this is where the protection comes on the electrical part. Because the solenoid valve is a component with suitable to hold the pressures for at least 10 bars of air pressure, the basis of the solenoid valve is that it's always well capable to withstand impact of dirt, typically water and moisture, because of its design to keep the 10 bar air pressure within the valve body. But the solenoid coil, with its electrical connection, it's not. So majority of the cases we're looking into an IP65 range, but higher rates are possible to be even fully submerged for longer periods of time. So first of all, the IP rating is an important factor. But this is not enough. With IP rating and the impact of water, where we see the highest risk within our applications, there's also considering the impact for ATEX. So if there are potentially explosive environments, the right selection for the solenoid coil needs to be considered. And we start always with the zone allocation. So from your application where the product is being used, this zone is classified into 3 different zones. So 1, 2, 1, 2 or 0, which is the highest possibility to have an explosion. And for dusty applications from zone 20, 21 and 22. And each of these categories, they have a product category, 1G, 2G, 3G. And these requirements are done through your risk analysis at the site to define the right ATEX zone, which defines the type of material and equipment that needs to be considered. Once this has been done, this can be done by yourself if you're a system integrator or an end user, or as a supplier, this information is provided to you as a supplier. The other part where considered is the explosion group. So even if we know the zone allocation, there's a certain group, 2A, 2B, 2C, which based on the medium that will be can be present, will generate a certain risk of the likelihood of an explosion. And this is not only the type of gas, but this also can do related to the temperature, which is related to a gas. Some gases or dust environments have a higher tendency to explode around higher temperatures or lower temperatures. One being the highest temperature, less likely to explode fast, or T6 minus 85 degrees already. So you can imagine with certain environments, this is very highly if you take this combination in mind. So how do we protect ourselves? So in the left bottom overview, there are certain protection cases that can be considered for protection of the solenoid coils in explosive environments. So EXT is, for example, a flame-proof enclosure where the housing of the solenoid coil is capable to allow for an explosion within the housing without exposure, without allowing any types of gases and sparks getting out of this housing, protecting the environment. But also a common technology is increased safety or intrinsically safe systems. Again, this is allocated with the blue cable glands and the blue cabling, where the power of the supply voltage and the current is so low that even if the wires are short-circuiting, they are not creating a spark that is strong enough to ignite the environment in which it's operating. Other than that, we have some moldings where the entire coil is provided with a certain protection and a resin in which it's being housed. So also any type of sparks or chances to ignite an explosion will be protected. And depending on the zone, one protection, of course, is better suitable than the other, depending on the analysis that has been done, and of course also on the decision for your budget and your design consideration. So there's always a selection or a cost benefit between the two, with of course in mind that the safety always needs to be assigned, but it's just an allocation of equipment versus technologies that can be considered. So this is one part. The other part, when it comes into demanding applications, is that when we actuate an actuator with a single solenoid coil, the chance that when the actuator fails, when the solenoid coil fails, can be really high. In this design, you see a single acting actuator, which means that we are using a 3x2 solenoid valve will be operating this actuator. When something happens with this system, the actuator will stop functioning and the process will be stopped. This is a single point of failure can result in an unsafe condition. This is not always preferred with the more demanding applications. So in these situations, we have the possibility to put multiple solenoid valve in series or in parallel. This is a so-called 1 out of 2 or a 2 out of 2 configuration, which means that if one of the valves is failing, the entire system fails, or you even can have a higher reliability that not even if one solenoid valve is switching by uncontrolled conditions, that at least in the 1 out of 2 of the solenoid valves need to operate before a movement can happen. So this is an additional level of reliability in your facility. With the 2 out of 2 design, one of the 2 solenoids might fail before the actuator stopped functioning. So if the bottom actuator, if the bottom solenoid valve fails, then still we have a second solenoid valve that is also able to provide compressed air to the actuator to function. So even if one solenoid fails, the system can still run and function. This is a little bit not as safe as the 1 out of 2, but this is more increasing the reliability of your installation rather than the safety level. An even higher level, and here we are talking more into the SIL 3 and to the SIL 4 applications. SIL stands for safety integrity level. We can even go up to 2 out of 3 designs. So here you see that multiple solenoid valves within the system and logics are being used to operate one single actuator. And one of the examples we see in the next slide is how we facilitate this. So first of all, to start with the 1 out of 2 or 2 out of 2 applications, here you see a NAMO interface with a specific interface block where the 2 solenoids can be mounted onto one block that can be connected to the actuator based on the NAMO interface design. So here we avoid a lot of tubing and a lot of additional equipment to connect the solenoid valves together, as you can see. Only an air supply and the 2 outlets are being utilized to be connected with the actuator. Another manifold, here we see, for example, the 2 out of 3 manifold. Here we see the multiple solenoid valves being used, pressure gauges to see the pressure of each and every solenoid, to measure and check the actual pressure and functioning of the solenoid valves. We not only use one single solenoid valve and don't understand if it's functioning or not. In this case, the pressure gauges are even showing a pressure rating if the solenoid valve is working, which requires a physical inspection of one of your maintenance team. We also can extend this a little bit further, and this is a 2 out of 3 manifold for HIPS applications. High ingress pressure protection system. And this is where we are also using 4 different solenoid valves, but instead of having individual pressure gauges, we are using pressure transmitters, which are the items shown over here. So these pressure transmitters can be connected to the DCS system to have an active reading of the functioning of the solenoid valves within the design, where we are, based on the performance, we can see how well the system is working. So these are mainly done for very high demanding applications where we have a single air supply and need to actuate one single actuator, but with an extremely high reliability. So especially in demanding applications, we see that we're not only relying on a single solenoid valve, but mainly on multiple solenoid valves within the system connected together. So this is on this topic. We're almost come to an end. Unfortunately, also we started a little bit later. Again, our apologies for this. But we will definitely keep on presenting more of these sessions. We like to share our information with you to help you in your work and benefit together from the knowledge sharing together. So if you did not follow us yet, please follow us on LinkedIn. We have a landing page, and follow us on our festo.ae and Flow. We have a YouTube channel, and of course, if you have some questions based on this webinar session, please feel free to send us an email to info_mina@festo.com. We would thank you very much for your time, and here are our personal contact details. And if you want to be so kind to, after the session, there will be a small survey. Please fill in the details, so also we understand how we can improve next time, besides our technical challenges, for which our apologies. But we would like to use this to improve our sessions for you in the future. Thank you very much. Wish you a great day, and trust to have shared some good knowledge with you. Thank you, and bye-bye.